Hi there. So our next topic is the chain rule. Okay, and this is a really fun rule, and it's also something which everything from here on out will build upon. So this is a really important rule that you make sure that you get a lot of practice with. Okay, so to motivate this, suppose we want to take the derivative of something like x squared minus 2x plus 5 raised to the 15th power. Okay? My hope is that there is no way that you would want to multiply out this polynomial raised to the 15th power. Okay? But that is something that we're interested in computing the derivative of. Another example, what if we want to compute the derivative of the square root of x to the 7th plus 3 to the x power? Or what if we want to compute the derivative of e raised to the x squared plus 5x power? Or one more example, how about the natural log of the square root of x? Okay? All of these are functions that we are interested in being able to compute the derivative of. Now, one thing that they all have in common, I claim, is that they're all actually the composition of two functions. Okay? So, for example, I claim with this first function, why don't I define r of x to be x to the 15th power and p of x to be x squared minus 2x plus 5. Okay? I claim that my function f of x is actually the composition of r of p of x. Okay? If you don't believe me, that's fine. Check this out. What does it mean to compute r of p of x? Well, you work inside out. In other words, we take what we define p of x to be, x squared minus 2x plus 5, and then everywhere where we see an x in our function r, we plug this in, and I claim you get f of x. Okay? So in this case, I claim that literally my p of x is my inner function and my r of x is my outer function. Okay, keep that inner and outer in mind. Let me show you how this translates over here. Okay, I claim that in this case r of x would be the square root of x, that this would be my outer function, and that my p of x would be x to the 7th plus 3 to the x power. Okay, I claim again that this is r of p of x. Okay, in other words, it's r of x to the 7th plus 3 to the x power. What does it mean to compute r of this? It means everywhere where we see an x in our function r, we're going to plug in x to the 7th plus 3 to the x. So again, this is my inner function and the square root is my outer function. Okay? Over here, I claim that my outer function is e to the x and that my inner function is x squared plus 5x. And I claim that this is r of p of x. Okay? Why? Because what does it mean to compute r of p of x? It means that we're going to compute r of x squared plus 5x. And I think you'll grant me that if we compute r of x squared plus 5x, we're going to get this function here. So in this case, my exponential function, e to the x, is my outer function, and this is my inner function. One more. Here, what do we have? I claim my outer function is my natural log function, and my inner function is the square root of x. And then again here we have r of p of x, because that tells us we're taking r of the square root of x. In other words, everywhere where we see an x in our function r, we're going to plug in the square root of x. Okay? So in all of these cases, what we have is the composition of two functions. So how do we compute the derivative of this? Well, I claim that's what the chain rule gives to us. Let me write out what the chain rule says. I'll write it out mathematically, and then I will also write it out in English. Okay, so when you have the composition of two functions, say f of g of x, and you want to compute the derivative of this, in other words, you want y prime, what you do is you take the derivative of the outer function, leaving the inner function alone, and then you multiply that by the derivative of what's inside. Okay? So specifically, if you have a power function, if you have some function raised to the nth power, this is your inner and this is your outer, the way you take the derivative is you take the derivative of the outer, leaving the inner alone. In other words, bring your exponent down in front, subtract 1 from your exponent, and then multiply it by the derivative of what's inside. If you have, say, e raised to some power, okay, remember this is your outer function, you take the derivative of the outer, leaving the inner alone. Well, we know the derivative of e to the x is e to the x, so it's e raised to that power times the derivative of that power. And lastly, we have the natural log of some function. Okay? Well, what you do is you take the derivative of the outer, leaving the inner alone, and we know the derivative of the natural log of x is 1 over x, so it's 1 over f of x times the derivative of what's inside. And notice this is simply equal to f prime of x over f of x. Okay, these are really important rules, and I totally get that they take a while in order to get the hang of. But the kind of mantra that you want to say to yourself is take the derivative of the outer, leaving the inner alone, and then multiply that by the derivative of what's inside. All right, so let's practice this, okay? So suppose, I can't remember the exact function I just wrote down, but something like x squared minus 5x plus 7 raised to the 15th power. Okay? How would we take the derivative of this using the chain rule? Well, I claim this is my top scenario. You take the derivative of the outer, leaving the inner alone. So bring your exponent down in front, rewrite your inside function, subtract 1 from your exponent, and then you multiply that by the derivative of what's inside. Well, what's the derivative of x squared minus 5x plus 7? You get 2x minus 5. Okay? Another one. What if we have g of x to be equal to x to the 7th plus 3 to the x power, the square root of that? Well, I claim that we could rewrite this as x to the 7th plus 3 to the power of x to the 1/2 power. This is square root. And then what we do again is we use our chain rule. You take the derivative of the outer, leaving the inner alone. So it's 1/2 x to the 7th plus 3 to the x to the negative 1/2 times the derivative of what's inside. Well, what's the derivative of x to the 7th? That's 7x to the 6th. And what's the derivative of 3 to the power of x? It's 3 to the x log 3. I'll grant you that it doesn't look necessarily very pretty, but here we have it. All right. What if now I have my function y equals e to the x minus 7x. Or excuse me, e to the x squared minus 7x. Well, we take the derivative of the outer, leaving the inner alone, and we know the derivative of e raised to a power is e raised to that power. And now we multiply it by the derivative of that power, which gives us 2x minus 7. What if we had just e to the 5x? Well, what would be the derivative here? It's e raised to that power times the derivative of that power. Now, some people might be like, well, how do I know when to use the chain rule? What if I just have e to the x? Well, it's not wrong to use your chain rule here. It's just a little bit of overkill, okay? Because if you're going to take the derivative of e to the x, you can use your chain rule. It's e raised to that power times the derivative of that power, but what's the derivative of x? It's 1. So you get the same thing. It's just working a little too hard for no good reason. Okay? Another one. Okay, well, before I do my next one, I'm just going to say this real quick. Again, how do you know not to use your chain rule here? Well, again, you can. Okay, the derivative of the natural log of a function is 1 over that function times the derivative of that function. But again, you just get that 1 over x. Okay? So I believe the example that I had written down before was the natural log of the square root of x. So why don't we go through that? Okay? And this actually simplifies in a really pretty way. I'm psyched to show you this. Okay? So let's talk about this. Well, how do you take the derivative of the natural log of a function? Notice it's 1 over that function times the derivative of that function. So it's 1 over that function times the derivative of this function. Well, what is the derivative of essentially x to the 1/2 power? Isn't it 1/2 x to the negative 1/2? Okay, so this gives me my derivative in unsimplified form. But what I want to show you is what it looks like when it's simplified. It's pretty cute. So check this out. Okay, we got this 1 over the square root of x. We have a 1/2, and if I bring my x to the negative 1/2 and I make that a positive exponent, I bring it down to my denominator. Well, look at this. We have a 2, and what's the square root of x times the square root of x? It's x. And you have to admit that's a pretty cute little derivative. All right. So, let's do this. I had some other really fun ones written down. Here they are. Just kind of putting everything together now that we've done in 3.1, 3.2, and now adding 3.3 onto it. What if I have y is 5 over 3x minus 1 over 2 root x plus e to the 7x? Yeah, that's good enough. Okay? So, what if I want to take the derivative of this? Well, the first thing that I would do is rewrite this so that I can take my derivative term by term. So that it gives me 5/3 x to the negative first power. We've got to bring our exponents up to our numerator. Minus 1/2 x to the negative 1/2. And for right now, I just leave that alone. Now, I see that there's actually only one place here where I need to use my chain rule. That's fine. Let's take our derivative here. What do? You bring your exponent down in front. That gives me a negative 5/3. And then when you subtract 1 from your exponent, you get x to the negative second. Second term, bring your exponent down in front. Negative 1/2 times negative 1/2 is a positive 1/4. And when you subtract 1 from your exponent here, you're going to get a negative 3/2. And here we use our chain rule. What's the derivative of e raised to the power? It's e raised to the power times the derivative of the power. All right, so let's just clean this up a little bit so we don't have any negative exponents. What do I get in my first term? I have negative 5 over 3x squared. Next term, 1 over 4x to the 3/2 power. And then I always like to put my constants out in front, so I would write that as plus 7e to the 7x. Okay, so here's a really nasty looking one, but it's going to be a ball. What if I have the natural log of x cubed, let's do this, plus e to the 5x minus the square root of e to the x squared plus x cubed plus 2 to the x power. And I totally don't want to simplify this. Okay? So, let's do it. Here we go. Y prime. Okay? What is the derivative of the natural log of a function? Well, you put the function in the denominator, and then you put its derivative in the numerator. Notice we're going to be using the chain rule within the chain rule. This happens very frequently. So what's the derivative of x cubed? 3x squared. What's the derivative of e to the 5x? It's e raised to that power times the derivative of that power. Okay? Don't start canceling these e to the 5x's. That's mathematically illegal. You're adding here. Another comment that I want to make about my first term is notice this natural log and this e. They do not cancel each other out here. You're taking the natural log of a sum here. You can't break up your log. Okay? So we got our first term done. Our next term, we're going to be using this top rule because when you're taking the square root, the whole thing is raised to the 1/2 power. So we take the derivative of the outer, leaving the inner alone. And now what we're going to need to do is multiply that by the derivative of what's inside. Well, let's do this term by term. What's the derivative of e to the x squared? It's e raised to that power times the derivative of that power. What's the derivative of x cubed? That's 3x squared. And what's the derivative of 2 to the x? That's an exponential. It's 2 to the x log 2. And it looks pretty crazy, but if you take these things and you do them term by term, I claim that they are actually quite doable. All right, I encourage you to get a lot of practice on this section before you continue on into the next sections. Thank you.